And let us today discuss the important ideas related to the compactification of extra dimensions in string theory. And these ideas originate from the so-called closure line theories. And this reminds me, before we do physics, Mr. Kaluza, I have forgotten his first name, I read it but forgot some years ago. He was from Lower Saxony, Niedersachsen. Mr. Kaluza was from Niedersachsen. And this Kaluza line theory, it dates back exactly 100 years ago, exactly a century ago, around 1920. So, and Mr. Einstein had recently published his general theory of relativity and had become famous. And this great friend of mine, if you could somehow David Hilbert, he was the mathematician par excellence, a great seat at Göttingen, and this guy Kaluza eventually ended up as a professor in Göttingen. So I mean, in those days, writing down the Einstein equations in the covariant form itself was a huge task. And David Hilbert, my icon, in fact he was the first one to write down the Einstein equations in the covariant form. 1 week later Einstein presented it at the National Academy of Sciences in Prague. Anyway, that's a different story. So the point is, Einstein was very impressed with Mr. Kaluza and he encouraged him to work on this. He was trying to unify the 4-dimensional theory with one extra dimension as a circle, and trying to see if he could unify gravity with electromagnetism. Of course, it did not work in the manner that we would call it a successful unification of gravity and electromagnetism, but nevertheless, you see, this idea of compactification of an extra dimension was really great. And string theory was not even born at that time. Nobody knew about what was string theory, or there would be some. It had to come much later. Actually, not to talk of string theory, even field theory was in the infancy stage at that point of time, 100 years ago. So field theory was developed in the next couple of decades after 1920 or around that. So the entire advent of quantum theory begins with Mr. Planck, and that is exactly 1900 when he talked about this quantum theory in the first place. Then quantum mechanics, quantum field theory, everything, and now string theory. So let's briefly recap. I would tell you in a very compact fashion because I always run short of time. So yes, so let me briefly recap the idea of Kaluza incline. Let us catch that particular point. Okay, so Mr. Klein happened to work in Sweden, in Stockholm somewhere, and Kaluza happened to work in Niedersachsen. Anyway, so that was 1920. Okay. Now let me quickly introduce a scalar field phi. Let me define it by the capital phi, and let me say that this is a function of f phi And this I want to so let us consider a theory in 5-dimensional space-time, okay, and flat space, no curvature, okay. So, and this field capital phi happens to be a function of these arguments, including x of phi, whereas phi m, which is denoted by small phi m, is a function of t and x. So, and this we separate out. I am x phi by r. So essentially what are we doing? We are making a Fourier expansion of the field capital phi, and these are the Fourier modes. Okay, phi m are the Fourier modes. Okay, m would be an integer, it will take values 0, 1, 2, 3 up to infinity, and therefore I would have infinite number of Fourier modes, and phi 0 would be my 0 mode, okay, 0th frequency mode would be phi 0. And now what we do is x phi we define as x phi plus cos phi r. Okay, so we compactify to 5th dimension x phi along the circle of radius r. Okay, so it could be given. So this is a coordinate on a circle, on the circle. Of radius r, and of course t and x are the coordinates of the 4-dimensional manifold. Okay, so t and x they span the 4-dimensional space-time manifold, and this 5th dimension is being compactified along the circle of radius r. Now what would happen? Now we could write down the equation of motion, and this would be, let me say, in 5 dimensions, capital phi t x and x phi, this equals to 0. Usually the Klein-Gordon equation. These are massless fields. They are massless fields, and so this is the equation. And here, or let me write 0 equal to this, and this I could write as minus del 0 square plus del 1 square plus del 2 square plus del 3 square plus del 5 square x phi, and this I could write as, this is my usual, so if you like you can denote it for the time being by 4 in the 4-dimensional D'Alembert plus phi. Okay, and now del 5 square phi, in particular, this would be, I have erased this by mistake, I would get iota m by r whole square times phi m. you differentiate it once, you get once this factor, you differentiate it twice, you get this factor twice, and this is obviously equal to minus m square by r square times m e to the power this. And so my equation of motion is therefore this equal to del inversion minus m square by r square capital phi. And so you see, this is the here it is in the 4 dimensions. Okay, let us not spend time on that. Now, so it is exactly this equation, and by if you put the value of phi m here, and this is non-zero, so basically what you get is phi m. Okay, what you get equation of motion as this, and these are the equations. So let me here mention for the modes phi m, and these phi m's are functions of t and x, and not x phi. So this is the wave equation. This as it stands here, this is the wave equation for a massive scalar field where mass is m by r, and in a 4 dimensional, in 4 dimensions. Okay, and if we consider, let us say, the Fourier mode phi 0, phi 1, phi 2, phi m, then what happens? The low energy observer is able to see only phi 0. Low energy observer would see only 0 frequency mode or 0 mode, phi 0. So you see, when if you want to observe so-called higher modes for m greater than 0, 1, 2, 3, okay, then in order to detect, there would be an infinite number of there would exist an infinite number of massive modes, m equal to 1, 2, 3, 4, 5, and so on. And in order to probe them, you have to probe theory for 1 by r at the scales of the order of 1 by r. If you probe the theory for the scales of the order of 1 by r, then you can observe these massive modes. Okay, and the low energy observer would see only phi 0 and not other states. So in a way, for the low energy observer, this circle of radius r is not visible. Okay, this was the idea, and in particular, if you define the momentum quantum mechanically minus iota del phi, then this is minus apply p phi on phi. This is this, and this is equal to phi. This is L by R into phi. So P5 here is the momentum along the fifth direction. P5 is the quantum mechanical operator, the way you define the momentum associated with x5. Okay, the canonically conjugate of x5 is P5. It's minus iota del 5, and this gives you P5. Phi is m by r times this. So what we deduce here is that the mode phi m carries a momentum m by r. What we deduce out of this is that the mode phi m carries the momentum m by r. And in order to observe these states for higher m, we need to prove this theory for the scales of the order of scales of the order of 1 by r.
Yes. That's phi m. It's not capital phi m.
This one?
Yeah.
Okay. Yes. Sure. Oh. Okay. This phi m. Okay. Good. So thank you. Thank you, Mathis, once again for this nice correction. And here I don't want to discuss more on this, and we assume what we have learned from this. Mainly we carry with us the idea of the convectivication. Of course, here it was not possible to identify the original idea or the motivation that Kulshreshtha line had was to consider a unification of gravity at the U1 gauge field, but this could not be interpreted as the correct U1 gauge field, which we understand now. So that way it was not successful, but this idea of compactification, you see, was to be used much later in string theory. We have many extra dimensions, and so let us now go into what we do with our string theory. Here, for the superstring theory, we will have d equal to 10 dimensional theory, and we will have 6 extra dimensions. So eventually we compactify them into a tiny circle of the order of the size would be 10 to the power minus 33 centimeters, or of the length scales, Planckian length scale. Okay, so it's a tiny ball, and again the low energy observers would not see it. Like if we consider a long electrical cable or wire and some fly is sitting on it, we don't see it from a distance. Okay, if you zoom it, and then you can see it. Okay, so this is somehow the extra dimensions can be compactified and into a tiny space, and there are many methods. We will not go into that, but now let us come back to this point where we left, corrected by Matthews, is our Virasoro constraints and Virasoro operators and others. And just to remind that this was P plus plus, and this was del plus x mu whole square. This was ls square summation over m and ln e to the power minus im sigma plus, and 0 equal to t minus is del minus x mu whole square is ln bar where Lm is 1/2 m minus n, alpha n, and lm bar is summation over n beta m minus n beta n. So we are assuming that we are taking a scalar product in the mu dimensional space time. Okay, so and these are okay. So these lm and lm bar are clearly the Fourier modes of these constituents. Okay, and I would not repeat many of the things that we have done before, but I would quickly come to let us say L0. We remember that when we have open string theory, we have only Lm and only alphas. When we have both the theory, when we have a closed string theory, we have alphas as well as betas, and we have Lm as well as Lm bar. Okay, because we have seen the relationship between alphas and betas. Okay, in closed string theory they stay separately. In the open string theory they get related. Once alpha is exactly equal to beta, once alpha is equal to minus of beta. Correct? With different boundary conditions and so on. So L0 is let us just consider L0 for n, and this is equal to 1/2 alpha 0 square plus 1/2, and here n or equal to 0 and equal to minus infinity to plus infinity. Okay, everything summation over all of them, and n equal to minus infinity up to -1, 0, then 1 up to plus infinity. Okay, and so I am separating them out. So alpha 0 square plus this alpha minus n, alpha n plus 1/2 n equal to 1 to infinity, and alpha n alpha minus n. Okay, here yes. So and then I could write this part h equals to 1/2 of n equal to 1 to infinity alpha minus n alpha n plus 1/2 summation over mu equal to 0 to d minus 1 eta mu like this, and this because you have shifted, you see, alpha minus m, let me put mu, this is alpha mu m delta. Okay, you know that because of the reality condition on x mu is x mu dagger. Okay, this tells you this. So if you shift it to this side, you get this factor, and this factor is equal to, this is d dimensional space time, so this is equal to d, and this is equal to minus 1 by 12, so that alpha 0 is 1/2 1/2 plus 1/2. So twice into 1/2 and n equal to 1 to infinity alpha of minus n alpha of n. So mu is implied, and plus minus d by 24, minus d by 24. So this is what we have, and so we remember, you see, this Lm and Lm bar are the Virasoro operators, and m goes from minus 1 to infinity. So you have an infinite number of these constraints operating on your theory. Okay, and you could simplify this L0. This is 1/2 alpha 0 square plus n equal to 1 to plus infinity, because we have added two of them. Okay? So that factor is gone, minus d by 24. So we keep this in mind, and one more thing we have to keep in mind, and that is the as I told you, that after the canonical quantization you have some commutation relations, in particular alpha 0 m, alpha 0 minus m. This is beta 0 m. This is equal to m beta 0 equal to minus m. So what happens is, because of this particular commutation relation in the alphas for the time-lag components, these are the time-lag components, alpha 0 and alpha 0. I had written for the, I need not write, or if you like, maybe I can write one, alpha mu n, alpha mu n, h and eta mu, and the same thing also holds for beta and from there this is what we right now want to use. So there would be some normal ordering contributions also arising from this, and eventually we will get rid of the negative norm space. What happens if you have a dagger, let us say k prime, you have delta k prime, you might recollect that we mentioned some such thing. So this is basically a dagger minus a dagger a equals to 1, or I have a dagger equal to a dagger a plus 1, right? So this is the normal ordering constant, and we want to take into account all of these normal ordering constants. What we do is we replace L0 by L0 minus a, and L0 bar we replace by L0 bar minus a, where a is the overall normal ordering constant, and this a turns out to be d minus 2 by 24 for the bosonic string theory. So this would be a equals to 1. Then we can, so we replace L0 by L0 minus a to take care of the normal ordering constants. Okay, and also to take care of the negative norm states, because what we do, so and this eventually this A is seen to be related to the total number of dimensions of the string theory. And then not only that, we demand that L0 annihilate physical states, L0 bar also annihilate physical states. In fact, physical states are defined to be those states that are annihilated by the constraints of the theory. Okay, and then we replace L0 minus A psi equals to 0. This I did not write equal to 0. This also I did not write equal to 0. This equals to 0 and this equals to 0. Okay. And so this equals to 0 and L0 bar minus A psi equals to 0. This is also equivalent to saying that the vacuum, the expectation value of this expectation value, so psi or so this is one and the same thing. Okay, if I say that the expectation value of this is 0 or this annihilates this, they are similar things. If you would look into the Gupta-Broiler quantization procedure in for electrodynamics in quantum field theory, you will see a similar kind of a situation where they demand such kind of a condition, or they call this kind of a condition. So this then would takes care for us all these points. And now, but we need to remember the expression for the L0 for us is 1/2 L alpha 0 square plus and instead of that, let me write L0 minus A equals to this minus A. Okay, so this would be for the open string theory, and for closed string theory I would have L0 minus A equals to 1/2 minus A, and L0 bar minus A would be 1/2 minus A. And for the closed string theory I would have two of these relations. Okay, this as well as this. And for the open string theory I would have only one relation. Okay, all right. And here let me mention it here. Alpha 0 mu is P R mu. Okay. Here alpha prime is LS square, or it's enough. Okay, so we could alternatively use alpha prime or LS. Okay, the two are related to, this is the radar slope and this is the square of LS. So now, and here alpha 0 is this and beta 0 is this. So beta 0 is P R mu and alpha 0 mu is P L mu. Where P L mu, P R mu are our expressions that we obtain. These two relations we are now, let me retain these two, and Now what we want to do actually, you see, we can consider what we have been considering so far. We considered the theories without compactifying any particular dimension, correct? So where does the difference lie? You see, here let me keep them separately, or if you like, you can write PL mu square. Similarly, 1/2 beta 0 square would be alpha prime by 4 P R mu P R mu. Correct? Now, and we know that this should be we use the mass cell condition. Mass cell condition would give me this PL square equal to mass square. So m square is PL mu or P mu in general, and for this you can say PL mu. It would be same also minus because of our metric. Okay, we have a metric with the signature -1 +1 +1, and so this is the mass cell condition that. Okay, and similarly this would be minus m square. This is whatever it is. So 1/2 alpha 0 square this is only one term. I should not make blunders. This would also be alpha prime by 4 into minus m square. And now we carefully want to make use of these relations here. And we keep in mind that in these expressions that I have just erased, mu is being summed up on all the dimensions from 0 to 25. And now we want to consider a case where we want to compactify the x25 dimension. We now want to consider the compactification of one of the spatial dimensions, let us say among the 25, x25. Okay, and as a result of that, what would happen here, that what we wrote here and for here, this would change, and that would change the mass spectrum, because what are we going to have is in the first place, let me explain to you the idea of compactification, and let us consider only closed string. So what happens is we consider only closed string and we consider compactification. Okay. Of x25. Let us consider compactification of x25 dimension. Okay, of x25 dimension. So for a closed string theory, x mu of sigma plus twice pi tau is x mu sigma and tau. This is for a non-compactified compactified dimension. Now what we want to do for x25, what we want to do is x25 sigma plus twice pi tau, we define it to be x25 sigma and tau plus twice pi and r. What we want to do is, we want to consider the compactification of the 25th dimension. So here we have x25. Now in general this holds true for all the non-compactified dimensions. Okay, and this is for the compactified dimension. So we want to compactify the 25th dimension along a circle of radius r. We want to compactify the 25th dimension along a circle of radius given by capital R, and here n would be the binding number. Okay, so we introduce a binding number, and we introduce another variable w, which is defined to be nr by alpha prime and r by alpha prime, and so this nr, this term, this could be plus 1 pi alpha prime w. So this could be written as this or that. So essentially we have only introduced this nr by alpha prime, a new variable given by w. And now I would need these relations a little bit later, but before that, let me as we have earlier done, namely we splitted our x mu into the as a sum of two left moving and right moving waves. We do it for x25. So we put mu equal to 25 in our general expression. So what you have is x25 L sigma plus, this is 1/2 x25 plus 1/2 alpha prime tau plus sigma, tau plus sigma, PL25 plus iota alpha prime by 2 summation over n alpha. For left we are using alpha, right? For right we are using beta. So alpha mu is now 25 alpha n divided by n e to the power minus in sigma plus. Okay, and you have x25r, this is 1/2 x r 25 plus alpha prime by 2 tau minus sigma p25r plus iota alpha prime by 2 summation over n beta n 25 e to the power minus in. This is taking too much space, so let me remove them for the time being. We have cleared them. So beta sigma minus. Okay, and from that what we do is we we want to write down x25, which would be, we want to sum these two. So what you have is 1/2 of this plus 1/2 of this. If you assume this equal to this, so you, or x25 plus alpha prime by 2 into tau into PL25 plus PR25 plus alpha prime by 2 into sigma into PL25 minus PR25 plus the modes. What we have done is, we have just summed up these two left moving and right moving modes along the 25th spatial dimension x25, and what we have obtained is the following. Now, because whatever we have learned for the non-compactified dimensions, that was true for non-compactified dimensions. For example, P25 for a non-compactified dimension would be continuous momentum. P25 is a center of mass momentum of the string, x25 is the center of mass coordinate of the string, okay, along the 25th dimension right now. But when we compactify a particular dimension, as we have done now, as we are doing right now, that we have imposed different conditions on x25. Therefore, we have got these two things separated out. This is called as the momentum mode, and this is called as the binding mode. And so we have to see what happens to the momentum mode, what happens to the binding mode, because for the compactified dimension PL, this may not be equal to this, okay, and so on. So this is the total momentum of the string, center of mass momentum of the string along the 25th dimension. Now we have two kinds of modes in the theory, and if I make a figure here, I want to leave them in for little purposes. We will see that we have two different kinds of modes. Momentum modes are these modes which lie on the surface of the cylinder. Okay? Cylinder is two-dimensional. They lie on the surface of the cylinder. Whereas the binding mode, they lie or they wrap around the cylinder. Okay, the binding modes wrap around the cylinder, and momentum modes, they lie on the surface of the cylinder. Okay, we will come back to them again and again. And now we come back to this, and PL25 and PL25, and so P25 is PL25 plus PR25, and we define one more thing. We introduce this as 2K by capital R. We define that P25 is 2K by R, where K is the Kaluza-Klein excitation, and R of course is the radius of the circle on which we are compactifying the 25th dimension. So what happens that the total center of mass momentum of the string along the 25th dimension now gets discretized or quantized. K is the Kaluza-Klein excitation number and it's an integer. Takes value 1, 2, 3, 0, 1, 2, 3 and so on. Without compactification, this P25 was always continuous, never discrete. Now, after this 25th dimension has been compactified, P25 becomes discretized or quantized. Okay? So, and so compactifying a dimension quantizes the momentum along that direction. Okay? Alright? It's the same thing. And for W that we introduced and R by alpha prime, this we identify with 1/2 of PL25 minus PR25, this one. So PL25 minus PR25 is 2W is 2L by R. Now we have to see the interplay between these two. The one is called as the momentum mode and one is called as the binding mode. Okay, and we want to see how would they affect our mass spectrum. I mean, and all other important quantities of the theory, for example, number operator. Okay, and how they get modified. In the first place, let us have a look at the mass operator. We already had that mass square formula, but the summation over mu was taking place from 0 to 25. Now, we would have to sum that mu from 0 to 24, because now the 25th dimension is not being considered at par with the other dimensions.